Hey, AP Chemisters, this is Mrs. Vanderlei bringing you the Blankwalle edition for section 5.5. This is the applications of the ideal gas law, molar volume, density, and molar mass of a gas. Probably most of you in your first year chemistry courses have talked about PIVNR, the ideal gas law that we covered in section 5.4. I'm guessing everyone has done molar volume too. That's your, well, I won't ruin your surprise there, but I'm sure you've done that before. I am not sure, however, if your first year chemistry course talked about density and molar mass of a gas. So this might be some new material for you in this section. So let's start off and talk about this molar volume. All right, so what is the volume of a gas at STP? Well, STP, what is STP? If I were to tell you an old joke, I'd say it is not Stone Temple Pilots. That may be a little bit too old of a joke for you. So what is STP? It's standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atm. All right. So let's go ahead and calculate the volume of 1 mole of neon gas, or really any gas, at 1 atmosphere at 0 degrees. So why don't you go ahead and plug in those values and see what you get. So pause this. Okay, welcome back. So what did we get? Well, here's what I got. So 1 atm times V equals 1 times 0.0821 times 273. So if you multiply 1 times 0.0821 times 273 divided by 1, look what you get. 22.4. Does that number sound familiar? That is the volume of 1 mole gas at STP. That is a big deal. All right. So this is the volume, of 1 mole of any gas at STP. Okay. And you've probably seen that before, haven't you? We've already used that. Now, can I just say this right now? This only applies for gases. It does not apply for solids or liquids. Only gases. So don't be tempted to use 22.4 for other applications when you're talking about volume. You'll probably need to use density in those cases and not 22.4, only for a gas. Did you catch all that? Did you write anything down to help you? So don't be tempted to use 22.4 for any other condition besides having a gas. Okay, so let's go on to the next page. All right, so it says, look at problem 11. Does it look familiar? This is the molar volume of a gas. Use the ideal gas law to convert quantities that are not at STP. All right, so if it's at STP, you're allowed to use 22.4. If it's not at STP, you got to use the PIVNR. So it says a sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles are present? So I want to do it two different ways. Notice I put a big or in here. I want to try it twice. So the first way I want to use is PIVNR. So it's at STP, so what's my pressure? 1 atm. 1.75 equals N times 0.0821 times 273. So do you have your calculators handy? What is 1 times 1.75 divided by 0.0821 divided by 273? What do you get? This is what I got. Okay, so I got 0.0781. Well, how else can I do this? We can do it by factor labeling. So what unit must go on the bottom is liters. What unit goes on top? Moles. And guess what? What's 1.75 divided by 22.4? Oopsies. Try this one. There we go. 0.0781. Hey, it's the same number, isn't it? Shockingly, isn't it? So you are allowed to use either way if it is at STP, okay? Do not use 22.4 if it's not at STP, okay? Let's see what the next question is. So assuming ideal gas behavior, all right, which of these gases will have the greatest volume at STP? So how are you going to go about doing this? Which will have the greatest volume? We have grams here, okay? So what can grams easily be converted to? Moles. All right, so really what this is asking for is which one has the greatest number of moles? Well, will that help me? Well, it sure will. What did Avogadro say? Do you remember the relationship between volume and moles? That was Avogadro's law. Is it direct or indirect? It was direct. Remember blowing into that balloon? Every breath of air puts more moles into the balloon. What happens to the volume? It goes up. So Avogadro's law says as volume goes up, moles goes up and vice versa. So if I have a greater volume, I'm going to have a greater number of moles. If I have a greater number of moles, I'll have a greater volume. So really, what is this question asking is what's going to have the greatest number of moles, all right? So what do you think I can do here? I bet I can set up an equation, or in a sense here, I can do this. Now watch. I'm not even going to use a calculator. I'm going to use my head. I'm probably going to need to do this. There we go. So which one is going to give me the greatest number of moles? The one I divide by a small number or the one I divide by a big number? Which one's going to give me the biggest number of moles? Well, I hope you see it is letter A. All right, so if you, I don't even use a calculator, folks. This would be a good multiple choice question now, wouldn't it? All right, so if I divide by a smaller number, I get a bigger number of moles. Okay, if I have a bigger number of moles, Avogadro's law says I'll have a greater volume. Okay, so that hopefully makes some sense to you. What about problem number 14? Again, no calculator. Oh, this might be a great multiple choice question, wouldn't it? So what is this? According to the reaction represented above, how many grams, periodic table, are necessary to produce the 0.50 moles of hydrogen gas at 25 and at 1 atmosphere? Okay, so, there's an equation. I want to go from hydrogen and talk about aluminum. What do you think I have to set up? Hey folks, begins with a B and it ends with a CA. All right, you need to set up a BCA table, all right, and see how that works. So let's check this out. If I start off with 0.5 moles of hydrogen gas, can I work backwards? 0.5 divided by 3 times 2 is 0.33. So how many moles of aluminum do I have? 0.33, or a third, don't I? Well, wow, it works out pretty nice, isn't it? So if I have 0.33 moles and 1 mole is 27 grams, what do you think I'm going to do? I'm going to divide 27 divide by 3 in a sense, or what's 0.33 times 27, and I'm going to get 9. So my answer is letter B. So if you don't believe me, go ahead and factor label it, but try to understand how you could have done that without using a calculator. All right, isn't 0.33 a third? And what's a third of 27? It's 9. Okay, so try that if you don't believe me. The next section is density. Okay, the next section is all about density. And what is density? Mass over volume. Okay, so what we want to do is manipulate the Pivnert, all right, so that we can get a density. Here we go, we can get density of it. So it says manipulate the ideal gas law to derive the density. So let me scroll up here, give me a second. So remember, I want to get mass divided by volume. Well, I have a volume right here, don't I? All right, so I need to incorporate a mass in here. Okay, so what can I do to both sides? Well, I want to multiply both sides by molar mass. Okay, and what else do you know about density? Density is an intensive property. Well, what the heck does that mean? I don't remember that from the beginning chapters. Intensive property means it does not depend on the size of the sample. So density is going to be true if it's for 5 moles, 100 moles, 0.002 moles, or 1 mole. Okay, so I'm going to make my life easier and say I'm going to assume if it works for 1 mole, it's going to work for any moles. Okay, so that's why I plugged in a 1 mole here, because density is an intensive property. It does not determine, or is not determined by the size of the sample. So if it's good for 1 mole, it's good for all moles. Okay, so I multiplied both sides by molar mass. All right, so far so good. I'm incorporating grams here, which I'll need to. Okay, and now what? Well, what do I have to do with volume? Oh, the mass of 1 mole is molar mass. There we go. I need to do something about volume. Why? Because I need to get volume in the denominator, don't I? So divide both sides by volume, and let me scroll down a little bit more here. There we go. So I have molar mass times pressure is equal to 1 mole times RT times molar mass divided by V. All right, so now what? Well, I think I need to get mass and volume by itself, so why don't I divide both sides by RT? Okay, so the molar mass times pressure divided by 1 mole times RT is a molar mass divided by volume. Okay, so what happens now? The molar mass is grams per mole, so what happens? The moles ends up canceling out anyway. And so here is my density. There we go. And it's equal to molar mass times pressure divided by RT, and then molar mass. Let me erase something real fast for you. It looks kind of messy over here. Erase, erase. Nope, what is that? Go away. Stop. There we go. And so I'll say it again. So density is molar mass times pressure divided by RT, which is equal to molar mass divided by volume. So I would use the left-hand side for any conditions that are not at STP. I would use the right-hand side if it is at STP. So now we have to always ask the question, calculate the density of nitrogen gas at 125 and a pressure of 750 millimeters of mercury. So your question you need to ask yourself, think of my voice in your head, is this at STP or not at STP? That is the question. So is it at 1 atmosphere and 0 degrees Celsius? No. So what side do we need to use? We need to use this side over here. So density is equal to molar mass times pressure divided by RT. So let's go ahead and plug in our values. We're talking about nitrogen gas. Isn't that N2, by the way? So my molar mass is 28.02 grams per mole. My pressure is 0.993 atm. How did you get that one, Mrs. Vanderwille? I divided this by 760, divided by R, divided by T. Now, I want to show you something. What's going to happen here? What can I cancel out? I can cancel out moles, can't I? I see that. All right. I can cancel out atmospheres, right? I can cancel out Kelvin, can't I? Yep. All right. What are my only units left? Grams and liters. So grams divided by liters, grams per liter. Isn't that a unit of density of mass over volume? Well, yes, it is, by golly. So 28.02 times 0.993 divided by 0.0821 divided by 398 is this. Okay. Now, if you have some room or get another piece of paper, let's calculate some gas densities while it's at STP. And that's your molar mass divided by your volume. Well, what's the volume at STP of 1 mole of gas is 22.4. So look how easy this is. What is the density of helium at STP? Well, it's its molar mass divided by 22.4, which is 0.179 grams per liter. I chose nitrogen as another one. 28.04 divided by 22.4 is 1.25 grams per liter. Notice that your moles cancel out. So what is oxygen? 32 grams per mole divided by 22.4 liters per mole, and I got 1.42 grams per liter. And then I picked, oh, why not, carbon dioxide. And then I picked xenon tetrafluoride. What a great gas there, okay? It is a gas. And look how big that density is. Now, I gave you the variety here because look at nitrogen. If I consider that 75% of the atmosphere is nitrogen gas, that is about the density of our atmosphere. It's a little bit higher, but not by much. So if I'm looking at gases, will they sink or will they float? Helium will definitely float in air. Look at that, 0.179 instead of 1.25. It's much less dense, so it's going to float. Oxygen is kind of close. It'll probably sink a little bit. Carbon dioxide definitely sinks. All right, that's why you can use it for a fire extinguisher because it's going to sink down. All right, and not only will xenon tetrafluoride sink, it's going to go thud. If you have a balloon filled with xenon tetrafluoride, it's going to go boink, 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 boink as the balloon drops. All right, so it's very, very dense. It's just going to fall like a lead balloon. Oh, I wonder if that's how I got that name. I don't know. All right, so anyway, those are some other examples for density. I'm about out of time for this installment, so I'll look for part 2 coming up. So don't wait to be great. Bye-bye.